Okay, so we're going to continue the lesson from class, and this is moving on to 8.5. This is a very, very quick and very, very small introduction of how work is done, and it is a very small connection to physics. All right, so work is defined as force over a distance, right? So force times the distance you travel, that's work you've done. So the way my teacher taught it when I was in school said that if you just simply hold on to a rock, you're not doing work because you're not taking it anywhere. But if you lifted the rock, then you did work because it went up a distance, right? The force that you're exerting on the rock plus the distance you lifted the rock, that's work done. But if you're just standing there holding that rock in your hand, you're not doing work. Even if it's heavy, even if you're sweating bullets, you're not doing any work. All right, so again, in this case, we're trying to discuss how work is being done and it has to travel over a distance. So then it connects really nicely to our integrals, right? Because you have to realize that your distance is not discrete, meaning that it's not like 1 meter, 2 meter, 3 meter. There's 1.1 meter, there's 1.111 meter, there's 1.09 meter. There's so many, infinitely many meters in between the whole numbers. So when you take the integral, you're taking all those numbers in consideration, which is beautiful because then you don't actually have to do it yourself. The integral takes care of all those numbers, right? So in this case, you can see the work done here is really the force here over this distance, all right? So again, apologies, there's a little typo here. So we don't need this second piece. Oops, sorry. Let me make sure I get rid of this. Okay, we don't need that second piece. All right. Okay, so what do we do now? Okay, so what we do then is set up our integral. Forgot that. Okay, work is defined as the integral 0 to 2, because those are my restrictions from 0 to 2 of x root 4 minus x squared dx. Okay, we're trying to take this integral. Now again, looking at this, okay, I see an x inside, I see an x outside, there's an x squared. So we got to use some tools that we had from before. We're going to use u substitution, right? So we're going to change this entire integral to a u substitution problem and go, okay, my u is inside the integral, so 4 minus x squared. My du is negative 2x dx. Remember to move that coefficient. Negative 1/2 du equals x dx. Next, don't forget to change your numbers, your a and b, to make it so that now it's with respect to u. So u of 0, I usually do the top first. U of 2 is 4 minus 2 squared, which is 0. U of 0 is 4 minus 0 squared, is 4. Okay. Once we have our u values, now let's rewrite our integral with all these u values, okay? So work is equal to the integral of root, okay? And that integral goes from 4 to 0. The 4 minus x squared is replaced by u. Now du is replaced by negative 1/2 du. Okay, now everything's in terms of u. I'm going to rewrite my integral so that it looks like a power rule, right? U to the 1/2 du, okay? So now if I take the antiderivative, I get u to the 3/2, multiply through the reciprocal, 4 to 0. Don't forget to reduce out the 2's. So you're left with negative 1/3. You can take that out as a coefficient as well. Okay, plug in your values. 0 to the 3/2 is 0. Minus, instead of plugging 4, I'm going to plug in 2 squared because that's a lot easier to clean up, right? And I can see that, the squares can't reduce out, leaving you with 2 to the 3rd, which is 8. So you're left with negative 1/3 times negative 8. So the work you've done is 8 over 3. Right? And again, typically there's some units, newtons per meter, newton meters, joules. But in this case, you don't have to worry too much about the units. Just kind of leave it as that. Right? Newton meters is kind of the standard unit, and it can also be written as joules. And those of you that are really good at physics, you can definitely help me out here. Okay. All right, this is a good one. This is just kind of talking about, looking at this as a big picture, right? Again, I'm not super great at this, but this is kind of a good practice to kind of approach physics from a easier standpoint, okay? All right, so it says a leaky bucket weighs 22 newtons empty. It is lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 0.4 newtons per meter. The bucket starts at 70 newtons, approximately 7.1 liters of water, but it leaks out constantly, right? So the bucket is leaking out constantly as it comes out, right? Just finishes draining as the bucket reaches the top. So it starts from the bottom, full bucket. As it finally reaches the top, completely gone. All right, so it's gonna leak out the entire time. Okay, find the amount of work done. So you gotta figure out what is being done here. There's a lot of things happening. So first thing, we gotta look at the bucket alone, just the bucket, and you don't want to look at anything else, not just the water, right? So look at lifting the bucket. So there's three things being lifted. There's the bucket, there's the water, and there's a rope. So we're gonna have to look at each individually and then combine them up. You have your total work. Okay. So lifting the bucket alone. So if you want to lift the bucket alone, you're looking at the fact that you're looking the bucket's weight is constant, right? If it's just a bucket, the weight is not changing. It's just the bucket going up and down. So there is a force and there is some distance, right? So lifting the bucket, keep in mind that the bucket weight is constant. And so, oh my word, sorry, I'm going to do something. Give me a second here. This is just really, really, really hard to read. Okay, let's try again. So bucket weight is constant. And so the weight equals the force, right? So it's right here. The empty bucket weighs 22 Newton meters. So then the work here is equal to 22 Newton meters, right? So the work here is going to equal the weight, which is the force, times the distance you lifted this bucket. So it's going to be 22 newtons times the 20 meters that you lifted it. So it's 440 Newton meters or 440 joules of work. Okay, so that's good for this piece right here. Okay, water. Okay, so the water itself, right, 70 newtons of water. So the water itself has some weight, but then it is draining as you go, right? So the distance that it is coming up is going to affect the water weight that you have in the bucket, right? So the force, see if that makes sense, the force that this water is being lifted, right, is equal to the water weight times the height that's changing proportionally, right? So the change so the weight is going to change, right? At the bottom is weight, it weighs at the bottom it starts at 70 newtons, but when you get to the top you have 0 newtons. You're going to take in all the weight in between, right? So first of all, figure out how this change happens. So the force of this bucket is equal to 70 newtons, okay? And then it's proportional, meaning at the bottom you have 100% of the 70 newtons. On the top, you have 0% of the 70 newtons. So at the top, at the full 20 meters, you got nothing. So if you go 20 minus x, minus whatever height you are at, over the total height of x, that'll give you the weight at that certain height. So let's say I am at 5 feet above the ground. Look at this, what's happening, right? If I'm at 5 feet above the ground, you are at 15 meters out of 20 meters, because this is, so 15. So I'm trying to, this is where I get a little bit stuck here. So when you're at bottom, you're at 0. So 20 minus 0 is 0. 20 minus 0 is 20. 20 out of 20 is 100%. So you have 100% of your water. When you're 5 feet above the ground, you have 75% of the water, because you're 5 feet, you only went up a quarter of the height. So you have 75%. How can you ensure that? 20 minus 5 is 15. 15 out of 20 is 3/4. So 3/4 times 70, that will give you the water force at that point, because you're 3/4 up. Okay, I'm halfway up at 10, right? 20 minus 10 is 10. 10 out of 20 is 50%. 50% times 70, you'll get 35 in the middle. So again, this is the proportion of the water that is changing proportionally to the height that you're going up and down. Okay, all right. Let's clean this up a little bit because this is not a very pretty equation to use. So 70 times 1 minus x over 20, right? I divide by 20 over 20. I divide x over 20, and then I distribute it to 70. So I get 70 minus 7 over 2x, right? Because 70 over 20 reduces to 7 over 2x. Okay. Now remember, you're carrying this bucket, this water is going up, right? And it's not going in what I said, just whole number meters. What about like 4.3 meters? What about 3.9 meters? So now we're going to take the integral. So the work done here is carried over from 0 to 20 meters, because from 0 to 20 meters, that's the full length, right? Of the force we just calculated, 70 minus 7 over 2x, right? And so that work of the force over this distance will give us the work, right? So this is dx, because our variable here is x. Okay, all right, this is nice. I can go ahead and take the antiderivative. I get 70x minus 7x squared over 4, because there's already a 2 down there. Evaluate 0 to 20. I don't need to plug in the 20 because I know that's a I don't need to plug in the 0 because I know that's 0. So plug in the 20. I get 70 times 20 minus 7 over 20 squared over 4. And if you want, put in the minus 0 so you know it's there, right? 70 times 20 is 1400 minus 7 times 400 over 4. So that gives me 1400 minus 700. So I get 700 joules of work for just the water alone. Okay, nice and easy. Okay, now what about lifting the rope itself? Okay, so if we look at the rope has a force of 0.4 newtons per meter, but your rope is shorter and shorter. At the full length at the bottom, right, it's 20 meters, but you're going to lift up, so you're going to shrink you're going to be shrinking that rope as it goes up. So it's going to subtract by the height you're at, right? Again, think about it. If you're a quarter of the way up minus 5 meters up, you have 15 meters left of the rope. If you're halfway up, you have 10 meters left. If you're 3/4 up minus 15, you only have 5 meters left, right? So it's a quarter left. So the rope, all right, let's see. The rope's length and width will change. The length and weight will change with respect to the height. So the rope length and weight changes with respect to height. Okay, so now let's figure out the force of this rope, right? So the force of this rope is equal to 0.4 Newton per meters, right? So 0.4 newtons per meter. And then how many meters is it, right? So it's 20 minus x, meaning that as the rope is going up, how many meters is it at each of the point, right? So again, if you want to write yourself a note, what is this formula saying? This is the weight of the rope times the height of the rope. Okay. Excuse me. Let's clean this up. And I get 0.4 times 20, distribute that. You get 8 minus 0.4x. All right. So again, just like the problem before, the work you're going to do is going to go again from 0 to 20 because that's the full height you're carrying this rope as well. And what is the force being exerted throughout this whole time? 8 minus 0.4x. And don't forget dx. Okay, so you get 8x minus 0.4. You can keep it at 0.4 if you want. So 0.4 x squared over 2, so 0.2 x squared. Evaluate 0 to 20. Okay. All right, so we're going to go ahead and plug in the 0 and the 20, right? So I get 8 times 20 minus 0.2 times 20 squared minus 0, right? Because the 0 is 0. I get 8 times 2 is 160 minus 0.2 times 400. So that's 160 minus 80, which gives me 80 joules. So now we're going to combine them. So lifting the bucket, 440, lifting the water, 700, lifting the rope, 80. So add them all together. I am doing a total work of 1,220 joules in total for this leaky bucket. Okay? All right, that's it, guys.